Welcome to today's Robotic Institute seminar. It is my great pleasure to introduce Professor Sangbae Kim. Professor Sangbae Kim is a professor of mechanical engineering at MIT, where he leads the biomimetic robotics lab. His research focuses on bio-inspired robot development by extracting principles from animal to the real robot. I'm sure many of you noticed great examples. MIT Cheetah, inspired by Cheetah, a quadruped capable of stable running at 13 miles per hour and autonomous jumping over obstacles. And a sticky robot, inspired by Gecko Lizard, a climbing robot that can climb smooth surface. And there are many other examples, like this one. And Sangbae has received many best paper awards, including ICRA, IEEE Transaction on Robotics, and IEEE Transaction on Mechatronics. And additionally, Sangbae received many other awards, just to name a few, to save time. NSF Career, DARPA Young Faculty Award, and Naga Mori Award. And finally, Sangbae gave many great talks in different venues, such as TEDx MIT, Davos Economic Forum, Amazon Mars Meeting, and keynote speech at Aeros 2019. I hope today is the next one. Without further ado, let's welcome Sangbae again.
Thank you. Thank you very much for a kind introduction. So yeah, I'm so happy to be here. I already met so many amazing people. CMU, I mean, I've been here 12 years ago. So, and I think I've been only for a conference. So I haven't actually really met people for a long time. And again, realize how amazing, how big the CMU is, especially robotics. I think robotics is just like no match. I mean, even like only a few places already bigger than other universities. And it's like I probably met only a fraction of people. I hope we can meet more. And I hope I can interact more after this talk too. So let's jump into the topic. So you might find a little strange as topic as a robotics talk. But I still think this is so important, even though how much you spend time in robotics, how much time you thought about this as a like maybe psychologist or even a cognitive scientist. No matter how much you thought about it, I still think it's worth still discussing. And it's important to set our direction in terms of our research in AI and so on. I've been talking about this. I thought about this like 10 years ago, and then actively started talking about this like 5 years ago, and then wrote article on IEEE spectrum and so on. So ever since like 2019, this is pretty much my talk. And that really gives us idea of what do you mean by physical intelligence. So let's dive into it. So the quick outline is I'm going to talk about how to build a robot outside a factory. This is pretty much summarizing my previous work at MIT and a little more. And then number 2 is basically the main topic of the talk. It's about human. It's not about robot. But it will help us to build a better robot. And I will talk a little bit about what I mean by physical AI versus virtual AI. And I'll briefly talk about future direction. So how to make a robot working outside a factory. You probably know that robot has a long history, 50 years history. Victor Scheinman, I'm not sure some of you know that, built the first programmable 6-degree freedom arm, and the company was bought by other company and become eventually Puma and so on. And ever since he designed this programmable robot, pretty much we evolved to build a robot like as accurate as possible in position control, and that became predominant protocol of controlling robot. Even in this era of AI and big data, we're still controlling robot in position. And I was very unhappy about the fact that we cannot use a robot outside a factory uncontrolled environment. I've been working really hard on to making robot available outside. I'm gonna skip this part because it's kind of too obvious to you guys. Like everybody have phone. I have 2 phones now, and physical services are just so different. But this is basically, if I say a little, controversially, this is more like a good to have technology. Just imagine some Instagram disappear tomorrow. What's gonna happen to your life, like daily life? Not your business, Facebook are mad at me, but think about what is going to happen to your daily life when maybe Google Map and Gmail is different, but for example, TikTok disappear tomorrow. Maybe I'm throwing too many companies out the door, but just think about any virtual services like pop up last 10, 20 years. It's kind of good to have technology. But just imagine a policeman disappear tomorrow, or a delivery person disappear tomorrow, garbage person disappear tomorrow, like a food shipping disappear tomorrow. It's going to directly impact our essence of our life, survival of our life. So, and we are getting into this crisis, like labor shortage crisis, global warming crisis. We have a lot of having real physical problem, and then we really need to think about how to develop AI on more like a physical side. So, what are the real physical services happening in our life? And these are pretty much what it is. These kind of robots servicing in the factory allow us to build a bio car at $20,000, $30,000, not $200,000, $500,000. Imagine all these cars are made by hand. Each car is going to cost like $500,000. So, these are pretty much not that different from nowadays. Even in this heavily automated factory, still human is doing as simple task as plugging in a electric wire, because robot cannot do this at this point. And this is what I mean by every robots are controlled by strictly position accuracy, position control, and there's no dynamic physical interaction. That's pretty much what it is. Even nowadays, I've been the most advanced factory where 43% of the operation is automated. They're still following this protocol of position accuracy, has satisfied under 100 micron accuracy. This is now like almost 10 years old video, 2015. DARPA just put out big challenge, and then a bunch of smart people going competition. There is amazing breakthrough in software, but if you look at the hardware, they're pretty much still factory robot. It looks like superhero, but if you look at the inside, all the structure is pretty much same as this robot. So in the early my career in MIT, I pretty much focused on how can I make this design paradigm shift from factory operation, optimized for factory operation, which means you're pretty much heavy, stiff. You can, so that no matter what weight you're picking up, you can achieve 100 micron accuracy everywhere. But as soon as you step out of factory, first of all, you cannot anchor your robot on the ground, concrete floor every single time. You have to balance. You have to move around. Your environment is going to be unknown in way more than 100 micron. It's going to be easily off by inches based on your vision noise and so on. You should be able to adapt. And there's so many unknowns. You can just command action with just position trajectory. So I was, the person who's sitting between robotics and biology, trying to learn from biology as much as possible. So these are a collection of my previous work. Probably what I'm most proud of is sticky bot still. I invent basically world first directional adhesion, which is actually how real gecko climb up. There's amazing science behind it. The robot is just cute. That's not the important part. The pad is actually the breakthrough in science. If I show you only the demo, so there's a directional adhesion on the plexiglass, and you don't need to push it. That's a typical case for double-sided tape. And then once you take the weight off, it just comes off. So that's actually how real gecko works, and much better than what I built. But if you do that with a double-sided tape, it only works when you apply pressure. And then once you get stuck, it's very hard to detach, because that's the typical pressure-sensitive adhesive works. But the gecko works completely differently because there's an anisotropic intricate structure that create van der Waals force very differently. So if you hang a 7-kilogram weight on the glass wall, I don't need to push it, but I was a little scared. And you can detach it with no detachment force. Like, if you look at the reflection doesn't even change when I detach it. Absolutely no. And Keller Autumn is a biologist who actually studied gecko, asked me to hang him on the glass, and I was like, "You're too heavy." How about my daughter? I was like, "Are you involving your daughter here?" So he actually drove his daughter from Oregon, and then we actually hung her on the Stanford wall without telling Stanford, but that was in History Channel. So, and I did some other running robot. This when I was a master's student. These are sort of inspiration how we actually extract the principle from biology, not copy nature. I still believe that in the even locomotion and manipulation world, we shouldn't copy nature. We should really try to just understand the principle and then apply it. And this is probably the most strange robot I ever built. It's called a mesh worm. It looks like worm, moves like worm. This is like the beginning of software robotics, and we developed our own custom-made SMA coils, and I learned how to anneal it, and heat treating and so on. And then this is more like aha moment. My student happened to be very heavy, and he's actually leading a robotics company in Korea now. And I was like, I gotta build something that's big enough and strong enough that can help human. That's how we start developing MIT Cheetah. 2012. This video is probably 2013, 12, yeah. And we didn't know how to build a balance controller. And I was very naive about the complexity of systems. So you can see the spine is still alive. When you see the transient gate, spine has become active. Still non-functioning head is bobbing. But we learned that this kind of actuation actually can be very, very useful. We were actually surprised how efficient this system was, because I was really laser focused targeting force bandwidth and force control actuator, not for efficiency. But it turns out that it's actually more efficient than other higher gear ratio systems. I will show you after what happened. These are pretty much summary of all the work from 2014 to 2019-ish. This is a Cheetah 2. This became finally famous and become balance itself, and then also autonomously jump over obstacle. Mike Graber said that, well, we still cannot do that. But this is more like a show of how actuation scheme has to be different when you step outside the factory, and how important to be compliant and at the same time observe shock, and also how quickly you should be able to control the force to interact with the world. I think I just added on because nowadays behavior cloning, teleoperation become really popular. This is we did 2015 with dynamic system, and probably some of you know the mini Cheetah that become pretty much blueprint of all the quadruped robot nowadays in China. This was 2017-18. This guy throw so much energy in IP opt and full nonlinear optimization and make the most beautiful gate controller ever known. And we started adding visions. We didn't do much of vision, but this is the kind of first time we kind of integrate vision and some rudimentary planning. And we had some fun with the Jimmy Fallon shows. And we built 10, 12 of them and then sent it out to the world. We literally assembled this whole thing in 2 desks in our lab. Our lab was very small, less than 1,000 square foot. But we were able to do this as a celebration. So the key idea is actually things called the proprioceptive actuation. Nobody called that. Now people start calling quasi-static, quasi-direct drive or something. So the reason why I'm not using that kind of term, because that doesn't represent actual importance of the actuation. So the idea is, are you measuring force externally and then feeding back, or are you going to do it internally? So that's why proprioception is actually very well used in the biomechanics community. All the encoders and force sensors in your muscles are actually proprioceptive. A lot of people think, oh, we need to have a tactile sensor measure force to be able to manipulate well. Your skins are not force sensors. Please remember that. Your skins are terrible at measuring force. Maybe you can measure some stretch. All your forces are measured by muscle. And we have such amazing transmission, so there's not much distinction, which is still a challenge. Anyway, so we kind of create a kind of Columbus effect, like a new type of paradigm of actuation. Now this becomes standard of the most leg robot that does anything dynamically. So this video has been This video we created probably 10 years ago again. It's a very old video, but it still shows how this kind of paradigm can do even things people conceived is not possible. This is a high force feedback teleoperation. And I feel all the forces and the other hand feels. And achieve this in very high bandwidth with no stability issue. But we use a zero force sensor here. Everything is proprioceptive. When I started MIT 2009, when Big Dog was like really popular and hydraulic robot is really, really like up in the air. And Italia started copying, then Chinese started copying, Korea started copying. Everybody's making hydraulic robot because, oh wow, electric robot motor is not going to work. Hydraulic is the way to go. And that's where I started the lab. And then I started developing the Cheetah I show you and the Cheetah 2. By the time Cheetah 2 was showing jumping and landing, people start making hydraulic robot. And then when Mini Cheetah was become popular, my student who developed the Mini Cheetah joined Boston Dynamics and then killed the hydraulic program. So Boston Dynamics stopped developing hydraulic the actuation scheme about like a year ago. And then, as everybody know, they start building electric version, pretty much follow our paradigm. Of course, there's a bunch of, I can add another 100 picture here who pretty much copy our paradigm at this point. And then, because there's no way, it's much, much cheaper, much, much reliable, and then eventually much more powerful. We need to figure out how to make it more accurate though. We still, there's things to do. But anyway, so proprioceptive actuation basically became kind of industry standard when it comes to interactive robot, not factory position accurate robot. Yet there's some companies that are still adhering to this high position accuracy, high stiffness, Tesla, Figure AI, and so on. Anyway, so in our lab, we build a robot kind of this way. We have a humanoid in the middle, but basically I can swap this robot out or whatever. We have a ping pong swinging robot, we have a manipulator, and we have a quadruped. They all share same hardware, basically. So if I want to build another robot, it takes like a couple of months because I already have infrastructure. It's like, that's important. These are not important, right? These we can just design in CAD, get it shipped and then assemble. Most important part is all these infrastructure, nerve system, basically. Or your communication channels and your motor drivers and power control systems, and so on. Let me briefly, today I'm not going to talk too much about technical stuff, but this is something I still believe in very strongly, and I think it's something we got to really think about as a researcher. I say there's an MPC, but that MPC can be replaced by search algorithm or a rule-based algorithm like that actually designed to be reasoning, pretty much any rule-based. And if you really think about it, I mean, like if you're trying to achieve something through a cost function, RL, my student takes 2 weeks to learn and then make robot run and walk, like take 2-3 weeks, make it work. But a lot of times it doesn't do exactly what you want. So you have to throw another cost function, make it run. If you look around, my video looks kind of stupid because if you look at Unitree video nowadays, it's amazing. RL can do a lot of stuff. But if you start adding other stuff, and then now you kind of get lost because this PPO is a very narrow scope. They cannot really cover many different things. But it's really powerful. It can throw like a sand on the ground, still can cover domain randomization, cover a lot of stuff. Whereas MPC rule-based, it can listen you very well. I can manipulate everything, but it breaks down as soon as you're a step outside of assumption because this region based on all these things. And if you think about, I just make a same step. I made the same step and then make another step. And I'd be acting like I don't know anything. I don't have any history, any no prior. I'm still reasoning. I'm gradient descent it every 5 milliseconds. It seems such a waste of computing. We need to take advantage of data. But the problem is data-driven many times, it doesn't listen to you. I don't know how to manipulate this thing. There's some knobs, but we don't know what that knob does. So I call that this is a very powerful monster, doesn't listen to you. This is a very obedient butler in your house, but cannot step out of the building. So we need to grab this butler and let it sit on top of this monster so we can control this monster better. So this is not just MPC to RL issue. Like any rule-based, like reasoning-based computational tool versus data-driven regression kind of tool. So if you think about it, if you know any plumbers or architect, they are always mixing these two. There's no architect came and I learned everything from book. Now I can build everything. They need to have knowledge. I've done this. This typically works. But they always face, no matter how the trivial the job is, they face something they never faced before. So they have to reason about it. But you don't want to reason about every single action because they're very time consuming and then it's not very effective because you assumption breakdown. If I teach you something, plumbing, in the book and then you start doing it, you're going to start with the wrong assumption. I assume this is, and then, oh, I didn't know that's going to happen. That's what reasoning algorithm does. Data-driven is very good at covering areas, but whenever you step into the area where there's no data, you have no idea what to do. But good plumber know what to do when in that situation because they know how to reason like an NPC. Just think about this as a really big picture tools we've been developing as a mankind. We need to be able to take advantage of both. Otherwise, you're never going to be able to cover all these spaces with the reliability. So we actually have an active project mixing these two. I don't have this is not the most exciting direction, but this is one example. Our reinforcement learning course is actually crafted out of the physical model. So it's trying to act like a physical model. What is the point? Because now we can actually manipulate this behavioral robot knowing that physical model we know. So we can actually manipulate in the direction we want it. That's not the whole story. We actually have another direction where we can actually combine all these QP solving tools into the GPU. So some people probably already heard about Kusadi. It's a CUDA, Kasadi running on CUDA. So that is kind of building block. Now we're actually literally throwing QP and all these sequential QP, MPC inside a neural network, and then we can co-learn everything. So that is a future, but this is a much simpler idea, model-guided reinforcement learning. So we can actually manipulate more than those cost functions we don't quite understand. And I'll also show pure MPC. This is a pure MPC, but it's all sequential MPC. There's no like IP up kind of thing. We're only using the convex MPC, but it's a sequential, so it can linearize in the narrow scope. But actually, it can do a lot of things well. That's the good thing about MPC. MPC, once you develop the core idea, now we can like make it step sideways, going forward, recording from jumping. It's all working because it's all physics-based reasoning. Of course, you'll fail if you step into the space where the assumption breakdown. For example, friction cone is not correct, and so on. Or your status measure is ziggling, and then everything go out the door. Anyway, so those are a quick summary of what I've been working on in our lab. I will show you a little bit of manipulation work at the end, but this is the main topic. Basically, I started talking about this because I guess I'm one of the beneficiary of this. Like I developed something, and a lot of people are excited, amazed by it, and then I listen to them, and they're misunderstanding. There's always a gap between what the demo really represent to people who doesn't know about robotics, and versus like what graduate student knows. Sometimes there's a huge gap between what professor knows to what grad student knows. That is sometimes useful when you pitch an idea. But anyway, it got into a situation where almost the entire community like hallucinating what actually AI can do and what the essence of AI is. So I started talking about this 5 years ago, and then I realized fascinating nature of human. So that's basically the main topic. First, we judge the performance AI in human standard. We are hardwired. We are evolved to be a social animal. Your dogs are similar, but being social, understanding each other is essence of essential for survival. So we evolved to judge each other, understand quickly by like looking at half second, and that's great. But the problem is that is actually influencing everything else, and then that's very very much what's happening in AI when we face AI, and we actually don't know what we're doing. And then I'm going to talk about a little bit of language, human language, and then I'll talk about quantity versus quality. Let's go. So I don't know if you can track your eyes. I'm pretty sure most of people looking at the backflip, and then what the hell are you showing here? I'm not sure how many people are familiar with the trajectory optimization and machine learning, model training, RL. Half? Okay, a lot of them. Probably you guys know where I'm getting at. This one took 3 days of 2 undergrad working in the lab, just part-time. This one took entire my team, at the time was 12 people, 10 people, working about 2 years. Of course, there's a hardware issue, like this one happened first and then this one happened later. But if you just think about like human perspective, that is a million times harder. I cannot do backflip. Or this is more energetic, that's more exciting maybe. But even before, like which one is more intelligence before, that is more impressive for you. And then you'd rather see that than this. And this is such a boring, especially nowadays. But just think about in backflip, as soon as you leave the ground, there's not much to do. So if you do proper optimization, push the right amount, the rest is just easy. Here, you have to watch out for your IMU signal, your state estimation signal every millisecond to decide what to do to stabilize your robot. And there's a lot of instability you have to tackle. But your brains are not wired to judge that quickly. You have to think a lot and talk a lot because we are not hardwired. Because balance is so easy for us. Probably some remember you, like just think about what you felt. I'm not asking what you think. I just ask you what you felt as soon as you saw it. Anybody want to volunteer? Say what you felt? Ooh, right? Like, oof, that was aggressive, right? That's a hard wire. No matter how long you work on robot, no matter if you're the one who actually developed, or even though you are the one who clicked this video, it doesn't matter. You're hardwired to perceive that aggression. Ooh, poor robot. What do you mean poor robot? That robot doesn't even have a spear, right? But that's how we are evolved. And imagine you see a lion chasing you in the mountain, and like you look at it like, I'm gonna measure the height compared to the tree next to each other, and then about 40 miles per hour, and then that must be about 300 kilograms, so it must be very powerful. There's no time for that. You're sensing 0.5 second, oops, and run, right? That's basically what's happening whenever you see a new video, robot video pop up in YouTube, and a half second, holy crap, that's really cool. So if you look at this video, if you go to YouTube today, if you look at the comments at the bottom, I guarantee you about 60% of comments are, you're the one who first person got killed by a robot when robot dominates. How dare you do that? Like, poor robot. Like, you're the meanest person in the world. Like, and when I first saw that, I was like, oh, these people are not very smart. Well, and then later I thought about it. It's not about smart or not what you know or not about. Not you know or not. It's about, it represents what human is. That's how humans are evolved, and then you can't get away with it. This is hardwired. And the point is that really dominate your perception about any AI or any robot. And like, yes, you can think and then you can logic. I'm smart enough to reasonably think about. Impression is emotion. You think about your VC or you decide to fund the company or not, you're heavily relying on the impression. Wow, that was impressive. I don't know, but that guy's very impressive.
Sangbae,
Yes.
I don't know if this affects your point or not. My reaction was, wow, that robot looks lifelike as it recovers.
Right before that. You're right before that. Like half millimeter before that. Yeah. Maybe you watched too many videos already, but I guarantee you somewhere in your brain, so that that was aggressive. Anyway, so anthropomorphism is basically dominating our brain, and then haunting us when you decide to feel that's great, that's or not, which one is impressive or not. It's ironic, actually, when I start giving a talk, like, I hope people make a better decision and then hope somebody don't take advantage of it. Now there's so many companies that take advantage of this, so I don't know what to say, but I don't think they learn from me. Hence Moravec's paradox, everybody probably know what that is. And if if you know what it is, just watch what the language they're using. They said computer exhibit intelligence test, something like playing checkers and difficult. And then they said it's a perception of ability. They don't even throw words. So they were already very biased about intelligence. What do you think the intelligence is? Are you guys biased? If you look at just the human history, people who know how to write, of course there wasn't a laptop at the time, but that determined like you're noble or not, who can control the country, like or not, right? Who can do the math? You remember like 1600, like 700, like who can do math? Like they're way above writing. These are the geniuses. I'm not saying they're smart. And like people who Isidore, like Isidore is a very smart guy, right? But we judge intelligence based on how good they are on these activities. And now you take a look at, that there's eye intention at a gap right there. Those things all covered by a computer now. Computers are better than us. Hands down, not even close. There's a number represent how good you are on the go. I think Alpha Zero is like 5,000 or something, and then the best human player is like 3,800.
37.
Yeah.
Yeah.
Not even close. And things we we kind of like look down upon, like, oh, he's a cobbler. We're not even scratching the surface. Just think about it. I just said that anthropomorphism is everywhere, and then how long for us humans to evolve to learn how to do this? About 10,000 years, maybe at most. It's arguable because when do we start talking? I don't know. But how long does it take for us to evolve to achieve these kind of stuff? Millions of years, hundreds of years maybe. If you think about basic function of muscle. But we are hardwired to appreciate and overestimate, oh, you must be smart because you're writing. Yes, true, in our standard. But is that the right standard for a clean slate intelligence or even a computer perspective, a robotic perspective? It's a completely different story. But we are hardwired to judge based on what is difficult for us and what is easy for us. And then we judge the capability of the robot. And if you think about a lot of those actions are very, very conscious because we developed later. We evolved to learn later, so it takes a lot of energy. And we typically call that a system 2. And a lot of things we do mundane daily, system 1, you probably wonder why this thing is sitting in the middle. I can tell you a little bit about it later. So another point I'm trying to make is we are so good at understanding this because it's conscious action, your 4 brains are involved. This one, you have no idea what you're doing because it's subconscious. You don't know what you're doing. How many people ate lunch? Okay. I don't believe many people ate carrot, but just assume you ate carrot. What happened afterwards? You bite a piece of carrot. What happened afterwards? You chew it and become small pieces and then go to your stomach so you can digest, right? How would that happen? Imagine if I give you a mock-up human mouth, and then you have a 2-cook arm there. And then piece of carrot, scaled carrot falls in, and there's a big chunk of like molar, like teeth coming in and out. How would you solve this problem? It's really hard. There's no camera inside the mouse. You grab this, throw it in, and then these 2 pieces are big, this small one I have to throw in the throat, and this is too big. I'm gonna throw it again, crush it, and there's spinach comes in, and you have to, and while doing what? You guys are talking to your friend while you're chewing. What did you use to talk? Tongue, this little piece of lump inside the mouth, doing all these things, you have absolutely no idea what your tongue was doing. Does anybody remember the trajectory of your tongue during your lunch. You have no idea what you're doing. I'll do one more thing. Bring something from your pocket. Bring hotel key, non-hotel key, anything. Right now, do everyone. You have to do it. Think imagining and doing is completely different. It's night and day different. That's why you do experiment, not looking at simulation. Grab things and then showing your face. You did it. You have to report back to your CEO, right? And I will ask you, I guarantee you, everyone use the index finger. Does anybody remember what your second joint of index finger trajectory? Or force profile, whatever we can say as a human language. You wouldn't even remember what the policy was. Do you know why? Because you guys are sitting on chairman's seat. You're the king. You don't know how the rice is grown and then how they cultivate, because you're the king. You're only commanding in high abstraction. Let's conquer that country, right? Right? You said, I want to grab something from a pocket. You're somewhere in the cerebellum, like doing some weird action. Is there any set trajectory? Every pocket is different. Every object is different. You don't even remember what your hand was doing. Some crawling, fidgeting. I have no idea. I still don't know what I'm doing. The point is, as I said in the previous slide, it's the unconscious part of your development. We have such a poor understanding. And I just proved it to you. You have no idea what you're doing. This might be cut out because a little bit of graphics. How many people heard about Mike the Chicken? Ooh, okay. Similar portion at Stanford. When I first saw this 2001 or 2, and then I was like, this must be a joke. This must be some urban legend. 1945, there's some farmer they probably kill chickens at least once in a day. And then one day, this chicken doesn't die. So it's interesting. And they start feeding through the hole in the throat and the waters. It survived more than a day. So I was like, okay, cool. I'm going to just carry him around and then make money. So that became famous Mike the Chicken. I didn't believe it until I saw this video. 2006, more than that, I think, 2008, or people started having iPhone everywhere. Same thing happened in somewhere in Africa, I think. And it interacts with the people. And this chicken doesn't have a brain. In fact, as you can see, it's a little graphical. I'm sorry about this, but it's not really a neck was cut off. The forebrain's gone. Definitely forebrain's gone. Your CEO is out. Cerebellum was there in the body. And one ear was in the body. So basically you cut the forebrain and then one ear, but the cerebellum and the one ear, which is IMU, is attached to the body and still functioning. And then perform like this. Of course, it cannot search for food or run away from predator, but it stands, walk, and then all the other biological function. And maybe you don't need the CEO, it's still working aimlessly. So all these functions you see is your forebrain doesn't involve. And we don't know how much our human function and how much your forebrain is involved. It might be creepy, but you are living in that bodies. But isn't that cool? You're all sitting in the CEO's chair now. But you have to admit that you don't know all the nitty-gritty details. So I took a video of my hand. What am I doing when I'm grasping? So I asked my grad student, like, can you take a video in slow motion? And then this is what happened. This doesn't happen every single time because when you approach this kind of object, I already have a prior. I'm picking fruits, and then roughly this size. So my hand is already set up like this. And then 70% of the time, it kind of like sit in the fruits. So I don't need, but this one happened once in a while. So I was curious what my hand is doing. It collide. Imagine if you have a good tactile sensor and maybe good vision sensor. What would you do here? Some search algorithm, like what is the best, closest thing, some heuristic, some cost. Probably pick the closest one. There are two top one. And then my hand was much, much dumber than that. It actually opened my hand. It's kind of have some reaction. If you touch something, open your hand. And then by doing it, pushing the best candidate out of the way. I was very disappointed. Oh. And then empty-handed. But while doing it, it ended up making contact with more fruits. I don't know if it's a pear or apple. I think it's a pear. I don't remember. And then even now, right, if you have some algorithm, can estimation of location of fruits, isn't this is the best candidate? Right? See what happened. It started digging somehow and then chose the worst possible choice. Rock bottom one. And then now put 3 fingers on, not 4 finger, I don't know. And then if feel like it's not secure enough, it plunge into deeper. Those finger actions are very delicate. I don't know what's happening. And successful pull out. So I was like, okay, that's pretty dumb. Right? Why would you do that? That's so much easier solution. And it does unnecessary work. But what's really impressive is this whole thing happened in 0.7 seconds. Do you remember how many decision-making change? Do this, change this, change this. That happened 0.7 seconds. Do I remember any of those? Absolutely not. I grab it and then apple is my hand. I don't remember any of these actions. So I don't know what to think. My arm is very dumb, but it does get the job done. Where's the intelligence is that like nitty-gritty optimization was good? It was even close to my grad student level. But the organization of the skills is just unbelievable, and how quickly we can execute. And my brain, 4 brains, are not involved with a single bit of it. If I pick up 1,000 apples, I'll probably show 1,000 successful, I think. I have a trust in my arms. Even though every step, how dumb that is, we get things done. Just think about where the essence of intelligence is. Is that great optimization? Great person? I wasn't even looking at it. I wouldn't even look at my eyes. So that's the end of the you don't know what you're doing. I had no idea what I was doing. And third one, language is extremely abstract. This double, triple pound upon, we don't quite understand what we're doing because we didn't develop human language to describe our action. What do you mean? I can teach everything. Yeah, anybody teach making peanut butter jelly sandwich to your kids or younger siblings, whatever? And by the way, do you think you can hand code it like an algorithm to do this? And you have to think about, should I command trajectory or should I command force? That's the only language we have. I have no idea, right? And how you guarantee spread well? Do I know viscosity of this? By the way, ChatGPT knows what viscosity is. It's crazy. Do I know how stiff the bread is? And which one should I do? What if you fling out the bread? How strong I hold the bread? I grab too hard, it's crumble the bread. If I hold too gentle, your bread slip out of the hand. Should I command position control? Should I command force control? But what would you say to your younger sibling when you teach this? Grab some peanut butter, spread. Spread well. More. Oh, good enough. What would you say more? Look at definition of the word spread. It all kind of makes sense for us. But if you're trying to make sense in the computer domain, in the ML domain, it's mind-boggling how abstract these concepts are. And we're okay with it. We're done. When that level, and then do it. Like abstract spread, and then your motor command coming out somehow. And then you're not losing. How come? I believe we have this magic piece of brain somewhere in the brain does all this job. I'm pretty sure there's some learning. I'm pretty sure some evolution. But we have this amazing thing called the mirror neuron that can take some impression, high abstraction information, and then execute. And then, of course, there's some learning. The 5-year-old probably had a bunch of mistakes, dropped the bread, everything. But as you're developed adult, we can do it really quickly. Of course, some things are very hard, like golf and tennis. Very unintuitive things, very hard. But we have this amazing mirror neuron. It's actually called the empathy neuron. We're not learning what the other person is doing. Also, we feel what the other person feels. Like if I do this, it's creepy, but you probably, some part of brains are like, I'm happy. No, you're not. This is just the fake. Some part of brains are simulating what you're seeing. That's why this phantom arm, have you heard about amputee who lost an arm? They feel the phantom pain. And even though you don't feel the phantom pain, if you go to that person, if you pinch your arm, that person suddenly feels the phantom pain. Because there's no counterpart to check that is real or not. If I do this, anybody feel the phantom pain in your arm? But somewhere in your brain you're simulating. But the reason why you don't feel the pain, because your arm said that's not real. That's not your arm. That's why the rubber hand experiment, exactly what it is. And this, I believe, is actually contributing a lot, probably not all of it. But the point is, because humans have evolved to be able to do this so well, we never need to develop a language to describe all this nitty-gritty stuff. If you show it, they will learn it. Just think about you're learning carpentry through a phone. I'm going to just call the best carpenter in the world, learn everything about carpentry. Do you think we can learn from it? I mean, they develop their own languages, but like our languages are so abstract that cannot have enough granularity or resolution to describe human action. Good luck, ChatGPT can solve physical problems. At this point, everybody agreed that. So people are working on VLA, virtual language action model. This is another kind of crazy example of human. I said clean tray. I didn't tell him graph of trajectory, whatever, force profile, and that's what he execute. Not clean up, clean more, clean better. That's it. This is how your brain is doing, from language to action. See the abstraction gap? Is how crazy that big is. Anybody who worked on robotics probably appreciate it. The hand is not even staying, it's skiing almost, like and get the job done. Fourth number, this might be the most impactful and pain you as a grad student. Human actually make decisions a lot more qualitatively than you think. And we can do anything without numbers with the computer. It's painful. A lot of leg locomotion is done well by reinforcement learning. And then one of the most important reasons, while the manipulation is still challenging because your cost functions are very easy to set up. We talked about that. Is it perfect? No, it's not perfect at all. In certain cases, when I got pushed, I'll probably do something like this, and then I can back up, right? My center mass drops significantly. But if you have a cost function, keep your center mass high up, this doesn't happen. And then might be easier to fall. But most of the leg locomotion, some parts where don't fall, some upper body hit the ground is penalized. But there are also density reward, like you have to keep up your body high center mass, orientation, right? Otherwise, your robot does something weird. So that is kind of proxy of a real goal. Real goal is to run smoothly well without falling. And then we don't know how to do it directly, so we create a proxy cost function, which is okay. It's good enough to put up a bunch of videos. Manipulation, all of a sudden, I don't know what cost function should I put on. Clean your room. Clean this dish. What cost function should I put there? Should I collect every single dishes and measure the amount of the dirt left and then supervise learning on this? You see what I'm saying? Like, how would you put a cost function to achieve manipulation task? Even safe driving, there's an expert here too, but like safe driving, what is a safe driving? I was thinking about driving, and then there's a curb, and then pedestrian, there's a 6-year-old girl standing, and then I was like, ooh, I should slow down. What is the chance of me hitting it at this point? 0. But I want to slow down because I want to appear safely. If you throw that on the computer and throw an NPC, it's not going to slow down. The chance of hitting her is 0, less than 0. Why you slow down? but you want to also appear to be safe, right? Clean your room. I cleaned it. No, that's not. That's not good enough. I have a fight with my spouse. Do you think we can set up a globalized, like globally agreeable, a bar which is in a chart, quantitatively written down, and then I'm okay with the level 3. Just think about it. We can take advantage of VLM to kind of do this, but fundamentally, certain tasks are so much harder to quantify the goal than others. And most likely, if the demonstration is done well, the cost function is very easy to set. What is the example? Go, Atari, language model, copy human nature, that's it. By the way, language, by nature, you have to copy. I'm speaking good English means you need to copy what English American people say. In order to speak good British English, you need to speak like British. There's no rule. But do you think you learn how to bring your things out of your pocket watching your fathers doing it and mimicking? It's a fundamentally different. Why? Because a language is a culture. You need to assimilate. You need to be similar. So you need to follow the rule of the norm of the culture. This thing, you have to follow the physics. You're not learning from mimicking. You actually need to obey the physical law, which is omnipresence. That's why we are so good at solving many things. Not everyone does, many people. Going back to the original topic, cooking yummy meal. What is the cost function? Why this one worked? Because cost function was damn easy to put out there. And some random action at some point is going to make it happen, right? So that is kind of a nice segue to really talk about divided between virtual to the physical. And that virtual might not be best word for some of you. Anything non-physical, anything living in your phone, anything you can do with your phone is basically virtual. Video, audio, text. That doesn't involve any physical energy. And there's just fundamentally different in every aspect. How you collect data is probably the biggest thing nowadays, a hot topic. One of the biggest things people don't realize, almost the like the most amazing AI we know, we think is very mature, none of them are autonomous. Do you know any LLM operating by itself with no human intervention? There's not a single hardware 100% run by ML or AI at this point in the world. There's always some human supervision. If there is, probably there's some more than ML, probably rule-based working there. And we can't really have any physical machine, human in the loop, still useful. There may be some. Still the LLM is useful. I can rewrite, I can work on my report. Your factory robot, I need to be babysitting next to each other. It's not very useful. They're fundamentally different function. And this is another huge difference. There's no uncertainty in virtual world. What do you mean? There's a lot of uncertainty, pixels and everything. No, I'm talking about execution side of it. My algorithm decided to spit out, I had a lunch. Sometimes doesn't come out lunch, sometimes breakfast come out, depending on wind blows. No, that's not the case, right? It's all bit, right? Digital. There's no uncertainty making. In the physical world, every 10 milliseconds, every 100 milliseconds is uncertainty. There's almost nothing is properly modeled. That's why I throw the autonomous driving right in the middle. There's a huge uncertainty in the perception side, but execution, there's very little uncertainty. If the planner is decent and then you put out the trajectory, chance of the car following the trajectory is very, very good, 99.99%. Uncertainty is on the other side, the decision making and the perception side. So that's why I think the collecting data to solve, many people today I met is all agree, just the human data is going to solve, and I'll tell you more about it. This is probably one of the most impressive videos I saw. I will just explain quickly only those who don't know about this. What's impressive is the recovering. I heard that it's actually recovery part is also trained, but the main takeaway point is amazing is recover, but only recover through the scenario. So those who, if you're not familiar with this kind of technique, just imagine you watch Indiana Jones 100 times. Why would you do that? No, just assume you watch Indiana Jones 100 times. And then if I show a second or two video, and then what's going to happen next time? And you will remember to tell me. But if I say, oh, at this point, Indiana Jones guy actually killed by the stone, rolling stone. What happened after? You have no idea. That's basically this kind of AI is. You have no idea outside of a scenario. If you think about, Gemini demos really impressive. There's some of them are really impressive, and I'm still trying to understand some of them. The tools are all different, but still, all these demo from human fall into this category. So to nail down the point, I'll ask this question. If I collect millions of people walking about 1 million hours, if I collect every single nitty-gritty data, even contact force, all the kinematics, do you think I can teach robot to walk? Humanoid. On flat terrain, because most data will be flat terrain. Do you think I can teach the robot to walk on flat terrain? How many people think we can make a humanoid walk with that data? How many people think we cannot? I don't know. Flat terrain, probably we can make it walk. Enough data. But what happens if I shove it? How many data points for 1 million people walking million data got shoved hard? Going back to the behavior cloning, dishwashing, any task you saw on the Google, Figure AI, physical intelligence, human demonstration data, how many of them are making stupid mistake and recovering, cleaning floor? And how on earth do you expect the robot to be able to be that robust and recovering from failure? Right? Maybe good for factory robot. Any question? Or?
You have like a lot of babies, videos of them trying to walk. It's a lot of recovering in the start.
Your baby how to learn how to walk? So there's a debatable, but I can tell you one thing. There are many ungulates. Ungulates are like horses and deers. They start running full speed about an hour after birth. There's a birds who live in like 40 meters above the ground, and there's a one day you have to first time fly, and then they're successfully flying the first time. Why humans are taking so long to learn? By the way, my kids, he fall twice before he start walking. So cautious, he's very careful, he's very not like risk taker. He fall twice and start walking. Just think about it. Like, yes, language. I'm very aware of the bitter lesson of the machine learning. I'm very aware of that. And language and some visual space where data is just abundant. Yes. I'm not really sure how well we can actually collect all the physical data to solve that problem. I'm talking about demonstration data. There's other way to collect data. There's other way to train it. Maybe some rule base will come in to fill those gaps. I can skip this. Oscar Wilde actually says that, which is impressive as a person who doesn't know anything about machine learning. Imagination imitate. It is a critical spirit that creates. As an artist says that. Really think about it. Imitation is not true learning. That's basically memorizing recipe to get the best grade, A plus grade from your class. That doesn't mean you're truly understanding. Do we need understanding for robot working? Maybe, maybe not. But for the things amazing robot we're thinking about, yes, probably we need to understand. I can give you just another idea. Tesla, I'm throwing so many companies under the bus today. This is the good side of it. 7 million cars, 7 million robots, that's robot, right? And 7 million teleoperator. They don't even pay. They actually got paid by them because they bought the company, the cars. 7 million robot with 7 million teleoperator, they're sending data. Not all of them, but many of them, right? And just think about car has a 2-degree freedom, and then deal with the one object, which is flat terrain, and never making break contact or making contact. And the task is also one, moving A to B. Whereas the manipulation, if you have one arm, not two arms, 10-degree freedom minimum, and your object's variety is infinite, your task is not infinite, it's a lot. How many teleoperator robot ampere do we need to match with the Tesla level? Which haven't finished yet. Tesla is not fully autonomous yet, right? Just think about it.
Somebody, can you continue this?
Okay,
We'll
yeah.
do some questions.
So, I mean, I am big fan of, already talked to several people making hierarchical, and basically, I am proposing to build a different layer, things we set as a subconscious level. The things we cannot express with human language. You need to build a new layers of a representation. And this is something we've been doing in our lab. And you probably guess what, can you explain this in human language, what's going on the left side? Do you think that's trajectory following or force following? We need to develop a useful function. There's something you can't even use, you cannot really, we cannot even describe, but it's useful for the function. So we're building a lot of these modules at the bottom level so we can actually really ground those suggestions from the ML or higher level planners. So we can actually get things done. So this video shows a real-time grasping. Grasping task is pretty mundane, but this is real-time, and there's no planning. Planning is like pointing the object, and that's it. And there's no large model because the low-level modules can handle this very, very quickly and quite reliably. So I don't want to talk about all these details. We call it reflex, but we need more than reflex. So we need like a lot more modules. We can make it hierarchical, so we can actually check and balance. Machine learning has to be accountable. We should be able to fix, improve, check what's wrong, and then patch up. If you have a giant model dealing with everything, I don't think we can do that. And elder care is one of the most impending issues. So I think we need to really focus on this to maintain our society. Thank you for listening, and I'm happy to chat afterwards.
I'm sure there are many questions. Any other questions?
Yeah.
It seems like at the highest level you want to use this reasoning-based cognitive.
Sure. Yeah. Yeah.
Do you think there's a space for embedding reasoning-based intelligence at a lower level, for example, using like motion primitives that we have a priori established are good, so we're not exploring spaces that are not helpful?
Probably. Yes, I think so. Yeah, like not everything is reactive and then adaptive like a lot of sports or even mundane job, there's certain things you have to practice well and then feed forward fashion, you're done kind of thing. I think there's a lot of those pieces will be there, I think. Yeah.
Between that and building this like intermediate representation where those things can be, for example, like listed as tokens in a higher for the higher level systems.
So yeah, I haven't really think about all the architecturing, but that communication channel, check and balance, is going to be pretty challenging. And I still don't know how to do it yet. Yeah. Like, for example, VLAs, like they're going to create amazing visual language action model, like even actions coming out. How can I take it and then use it? Or when things goes wrong, and then should I ask it again? Should I fix it by myself? It's kind of similar to how you build a company. You have a CEO, CTO, CEO, and then it become hierarchical somewhat. And how are you gonna communication? Like building a hierarchy is not hard, but you have to set up protocol of escalating and managing and all that, right? Yes.
I'm curious about the reference layers.
Yeah.
So, for example, for safety check, do you think that's a better way to embed explicit physics rule or some other implicit learning? Because I think for human or for me, I feel it, right? The thing whether it's going to fall or not, instead of like
you have
actually
amazing prediction
doing
model.
the force analysis. So,
Good
what do you
question.
think about the learning? Like which layer that we want to see that?
I don't have a great answer, but I'm pretty sure we need multiple. Good prediction, the good planner. But also when things go wrong, there's like when you're driving a FSD, you're not driving. there's a system actually, kind of NPC kind of system are watching, and when things go wrong, it alarm. Those are usually happen when I'm driving, but they even happen in FSD driving. So there's separate system. They're like, alarming system. You're about to hit something, for example. And so I think that's kind of like a third net. We need probably multiple net. Like first net is you plan really nicely, knowing all this dangerous thing, but also you need to check, like even though there's some once in a while making mistakes, you have another safety net. So when it's about to hit something, pause or modify. So it's somewhat similar to actually like laws. There's always multiple nets to catch and then fix. I'm pretty sure self-driving has a lot of those check and stuff. I know some company run ML rule-based, and when things are going haywire, this one stops and overcome or mix. Yeah, we need the multiple layers so they make it really safe. Yeah.
Using this reflex layer to kind of bridge just like high-level reasoning, like high-level control, and I kind of like. This might just be like stemming from a personal experience, but it's like if I'm dropping like a box or something, or like I feel like maybe like a knife. Like if you're cooking and you drop a knife, your first reflex is to immediately like try and catch the knife, even though that's probably not the smartest thing to do long term. And I think like if you're doing something that's hierarchical, it's like how do you bridge kind of this like when you should rely on reflex versus when you should rely on control. And then it's kind of like, do you have any ideas in terms of how you would approach kind of dealing with that like intercommunication between the layers?
That's a very good question. Short answer, I don't know how to do it yet. Like that's a great question. If you drop a knife, would you catch it? What if you cut your finger, right? So that's a good example. That's basically the problem of the multi-layer system, right? If you're all end-to-end, you somehow figure it out. And once you're hierarchical, now you need to communicate between them, right? One of the reasons why I want to have another layer at the bottom, not only I want to check the safety kind of thing, also I want to minimize the gap between sim to real, because it's its own self-contained feedback policy. So as long as you get things done, if there are difference, but your question is, I'm not even thinking about it right now. I'm pretty sure it's going to bite me butt later. So I need to think more about it. It's a good question. I don't have a good answer for that. Yeah.
Okay, 2 more questions.
Yeah.
Beck?
Yeah, thanks. That was a super fun talk. I wanted to ask, like, sort of building on this question, a lot of the hierarchy that we talk about in these systems, like we talk about these biologically. Biologically, a lot of these things are coming from hardware limitations, right? They're coming from the fact that we have a lot of latency and we're slow and this kind of stuff. So we have these kind of reflex responses to overcome the limitations of our hardware. But on these robotic systems, we can make amazing, kilohertz bandwidth at the lowest levels.
Yeah.
So I guess I'm asking, like, what are your thoughts on this? The fact that we can make better hardware than the biology, and that's faster, lower latency, does that at some point eliminate or reduce the need for these hierarchical things or these reflex things?
So the main reasoning for hierarchy is actually not because of delay, like mimicking biology. I'm a big fan of not mimicking biology. It's more of the grounding issue. What the big model is giving me is too abstract or too uncertain, and I have no idea how to ground it. That's why I want to have a separate layer to ground it. Like, for example, VLA, somebody made it, and then, I'm using it, and then it made a mistake. What I'm going to do, call the company, can you update? How many $100 million to cost to fix that? Whereas if you have another layer, we can take care of that there. So kind of very similar to, CEO, ask something, and then the department take care of it by itself. Not necessarily because it's slow. It's more like a local thing. I'm pretty sure safety kind of thing, like when local algorithm try to catch it, that's reflex. But the somewhere high level, that's a blade. Don't touch it. That can command with no delay. So that can sit. I don't know where it's going to sit. That's going to probably sit at the top. Safety thing. So the hierarchy is more of the grounding, the more abstract planning concept rather than speed issue. Yeah.
Okay, let's have the last question.
You were splitting the physical and cognitive skills, and then you're also harping on manipulation is hard because it's hard to express the cost function. And then you're talking about grounding, so task and motion finding sounds like something to think about. So where do you think the role of like building the skills that we're good at, are they just skills where we've built the right abstractions so that we could express them in tools that we have ways to solve, and the skills that we don't have yet are the ones that we don't have the right abstractions for? We don't have the cost function, we don't have the data, we don't have the solver, because we don't have the right abstraction.
Great question. I mean, I don't have an answer for that. I just observe there's fundamental difference between human and machine. And I would say I don't know how to architect that. I can give you another example. A lot of people misunderstand evolution is optimization process, which is not. A lot of people hear that survival of fittest is a completely wrong sentence. It's the survival of happen to be good enough. There's no gradient above it. Once you pass it, you pass it. There's no gradient. Once you pass it, I don't know where to grow next time. There's no gradient. Biology's evolution is just, as long as you survive, you're done. You don't need to be the fastest animal in the world. You just need to fast enough to catch your prey, which could be a bug, right? Cheetah happened to chase gazelle, so it has to be fast enough. So humans are operate kind of that way. Like if you go grocery shopping, like how would you decide to buy what grocery today? Are you measuring and then following gradient descent? No. It's mostly, good enough. I'll buy it. So a lot of them are just passing a bar. It's more like a feasibility search. And we don't know how to program things in a feasibility search way very well. So it's more like an architecturing issue than representation. I mean, representation could be important, I think. Some people don't believe it, but great question. I don't know enough that answer
I
that.
really want
Yeah.
to ask a question for student. So what do you think robotic students should work on today? Just give us some give students some high advice.
This is a kind of curse of academia. You have to learn everything, and then I'm not even catching up with the what everything's going on. So try to learn a lot of things and step back and then think as a big picture problem. Like think about I said about MPC versus what is data driven, what is rule based. What are the pros and cons? Don't pick like this is better, more trendy. No. What is fundamentally different, and how you mix this to actually make a better progress.
All right, let's thank Sangbae again. Yeah.
Thank you.